Hello again, physicists! It's great to be back. Today I have a special video for you. We will be working with something called dimensional analysis. And what is dimensional analysis? Well, we're going to use it to determine the validity of a solution in physics by using only units. Yeah, I told you earlier, units are your friend. You need to know your units. We're now going to begin to see why units are going to be so friendly to us as long as we know them. So to begin, here's the process for how we will use dimensional analysis. It's a two-step process. First thing we're going to do is we're going to plug in the units of every input. And when I say input, I mean the things that you would plug into an expression. In our examples, you'll begin to identify pretty easily what an input actually is. All right, and after you have plugged in for every input with a unit, we are then going to use some algebra. And with that algebra, we're going to reduce the units that we've put in from step 1 to see the final answer, and what our units will be for that final answer. So again, the units we see in the end will be the units of our final answer. And if we know our units fairly well, that means we can then see, all right, is this equation really going to give me the quantity that I wanted? So as with most things in physics, it's easier to actually see something being completed as opposed to hearing me talk about it necessarily. So we're going to get straight into examples using dimensional analysis. The expression that I'm using for this example is one that we will deal with in kinematics, our upcoming unit. The way I would read this is that the position of something, which is the x here, will be equal to its initial velocity multiplied by time. And we're adding to that 1/2 of the object's acceleration multiplied by that same time squared. And all I'm going to do here is I'm going to check and see, do the units on the left-hand side match up with the units once reduced on the right-hand side? So I have to ask myself, okay, for position, what would I measure position in? Well, my SI unit for position would be the meter. And I just want to know, okay, well, do the units of everything over here on the right-hand side, when combined together, do they give me units of meters as well? Because if they do, it then means that, yes, this is a correct expression for being able to determine the position of an object. So on the right-hand side, I'm going to start plugging in units for each of my quantities, starting with that V0, which is initial velocity. The units for velocity are meters per second. And we are multiplying that by the unit for time, which is seconds. All right, and to that we are adding 1/2 multiplied by the units of acceleration, which are meters over seconds squared. And that is being multiplied by units of seconds, and we cannot forget that this time is being squared. Therefore, my units of time will also be squared, so it's going to be seconds squared. Okay, so this is step 1 right here. I have completed step 1 of my two-step procedure. The next thing I'm going to do is now reduce this, and we're going to figure out on this right-hand side, what do all these units really shake down to? And again, if it comes out that we only have units of meters ultimately, then it means we have a good expression here. So I'm just going to rewrite the left-hand side of my equation. And now let's start doing a little bit of algebra. So I have meters over seconds times seconds. And if you want to put that over 1, that's fine because technically it is over 1. And hopefully now you can see that the seconds are going to cancel out in our first term, leaving us with just meters. And then in the second term of my expression, I have meters over seconds squared. And we are multiplying by seconds squared, which again we can put over 1. And here we can see that also, hey, these seconds squared, they're going to cancel each other out. So what I'm left with now is I have meters for the units in my first term, and I have a half times units of meters in my second term. And hopefully we know that if we add together two numbers with the same unit, the result will also have the same unit. So when I add these meters with these meters, my outcome unit will still be meters. So guess what? Doing dimensional analysis, it checks out. The right-hand side of my expression leaves me with units of meters, as does the left-hand side. So that means that this expression at the top here is a valid expression. It is a way to determine the position of an object. Here's a second example for you. This one is going to be a little more involved in terms of doing the dimensional analysis. So we're going to take a little bit more time to walk through this second example. What I have here is an expression that we'll use probably in our third or fourth unit involving the gravitational force between two massive bodies. And just so you know, on the left-hand side, I'm going to identify the units for my answer. The units for force, if we break them down into fundamental SI units, would be kilogram times a meter divided by a second squared, or a kilogram meter per second squared. And now on the other side, I'm going to just check and do a dimensional analysis on my expression and make sure that indeed it will provide me with appropriate units and therefore allow me to know that I'm actually finding the gravitational force in this case. So to plug in my units here, capital G in this formula is actually a constant, and the constant has units of, get ready for this, meters cubed per kilogram times a second squared. That's just for this big G right here. Okay, then M1 and M2, these are two separate masses. So we know that masses will have units of kilograms. So I put a kilogram in for M1. I put a second kilogram in for M2. And then the whole expression will be divided by R, which is going to be a distance. Therefore, I'll use the unit of distance meter and replace R with that. And then we will have that meter squared. So again, there is step 1 completed. Now we just need to take all these units and do a little bit of algebra and see what do we end up with. Looking at this, hopefully you can see that these kilograms, if we were to multiply in the numerator, they would be up here with the meters cubed. And because of that, that means that one of these kilograms will cancel with the kilogram that I have in my denominator here inside these first set of parentheses. And then that just leaves me with the meters cubed times the kilogram. Okay, and that's all over a second squared. And then we're dividing that by the meters squared in the denominator of this expression. So divided by meters squared, which we know is the same thing, really, as multiplying by 1 over meters squared. Okay, now you can see that the meters squared will cancel 2 of the meters I have in my meters cubed. And what I'm left with will be kilograms meters over seconds squared. And guess what? Aren't those the same units I had on the left side of my expression? I think it is. You know, kilogram, kilogram, meter, meter, second squared, second squared. So again, dimensional analysis worked out. We've confirmed that, you know, this top expression here is a way to determine gravitational force. All right, now switching gears, I'm going to show you a second way, and a very important way, in which dimensional analysis will also be useful, specifically when it comes to graphs. And we actually did this once in class when we were doing graphical interpretation. So for the example provided, we have a plot of velocity in units of meters per second versus time, which has units of seconds. And just keep in mind that, again, this is our y-axis and this is our x-axis. And I have a line on here. Could be a best fit line from some data that I took. And let's say that we wanted to figure out what the physical meaning of the line is. Well, we know from math that if we wanted to take the slope of a line, it would be equal to the rise in our line divided by the run. And we have to remember that that means, and specifically, we need to look at what variable is associated with our rise and which variable is associated with our run. Well, in this case, our rise will be the velocity, and the run is time. Okay, we can now use dimensional analysis where we plug in units for what v and t are, and we then can reduce those units, and we'll have what the units of our slope are. So let's do that. So we're saying our slope units will be equal to, okay, well, the units of my rise, units of v, would be meters over seconds divided by the units of my run, which would be time, seconds. And now I'm going to take this and I'm just going to reduce it. So we have meters over seconds, okay, and that's divided by seconds, so this will be the same as multiplying by 1 over seconds. Okay, so it looks like the units for our slope will be meters per second squared. Those are the units for my slope in this case. And if I can just remember, you know, what quantity has units of meters per second squared, then I'll know what quantity this particular slope is representing. Okay, well, meters per second squared are the units for acceleration. So guess what? This particular slope for this graph is telling me, based on my dimensional analysis, that the slope is going to be an acceleration. So here's another handy way in which we can use dimensional analysis to get meaning from our graph. All right, folks, so we're going to use the same graph now, but I'm going to get an interpretation of the graph by doing something different. So far in class with graphs, all we've done is really talk about taking the slope of a best fit line. Well, there's a second approach with graphs that we're going to use throughout the year that will additionally give us physical meaning, and that is taking the area of the graph. And by that, I mean if we have a plot with a line or something like that, if I look specifically at the area underneath the line, sometimes that has a physical meaning as well. And we can use dimensional analysis to figure out what that physical meaning is, just like we did with the prior example. So we already talked about how in the first example, you know, slope was equal to rise over run. Here we're going to think about the formula for area. And then we'll plug in units for the input for that formula for area. And then we'll take those units plugged into the expression and we'll reduce them and we'll see what physical meaning does the area underneath this line. Or in other words, what does the area of this shaded region, what does it mean to us? So, hopefully we know that the area of a triangle would be 1/2 base times height. Okay, so what I'm going to do now is similar to the prior example. I'm going to figure out what the units for area are for this particular graph by completing a dimensional analysis. All right, so the 1/2 wouldn't really change. That's just a constant. All right, let's look at the graph. If I think about the base of my triangle, that would be this part right here. Okay, so which of my axes runs from left to right? Well, that would be my time axis down here. So my units for my base will be my units of time. And I would plug in an S for seconds. And then the height of my triangle here, my shaded region, would be, looks like that would be running along my y-axis. So I'm going to put the units from my y-axis, my units of velocity in for height, which would be meters per seconds. And now my last step would be, again, to reduce the units, do that dimensional analysis, and see what the units for this particular area would be. The seconds would multiply into the numerator, so that means I would have a seconds in the numerator and another seconds in the denominator. This leaves me with units of just meters. So now what I could do is say, all right, well, if my area is going to give me units of meters, what physical quantity has units of meters? And the answer is distance, or displacement, or position. So again, we use dimensional analysis to take our graph, in this case take the area underneath our graph, and give it physical meaning. In this case, this shaded area actually tells us how far the object traveled. So that's it for dimensional analysis. Tomorrow, make sure you come in with any questions that you have. And with that said, physicists, till next time.